right, so this week we'll start off with section 3.7. This is kind of separate from everything else we're going to do during the week. So this is on solving systems. All we're really going to be doing in this section is calculating where two graphs cross, okay, using the graphing calculator. And then we'll move on from chapter 3 and start what we're really going to focus on this week, which is chapter 4. All right, so just a reminder what a system of equations is. Okay, it means that we're solving for multiple variables. Okay, so it's when you have to solve two or more equations for two or more variables. Okay, so you're not limited to two. I mean, you could have a problem that you have to solve for 3 variables or 5 variables, okay, all kinds of variables. But the problems we're going to do are going to be limited to just 2 equations with 2 variables. Okay, and most of it we're going to do graphically. I think there is one problem we'll look at algebraically, but most of it's going to be graphically. And if you're looking for the solution to a system with 2 variables and you graph it, it's an ordered pair. Okay, you're basically looking for where 2 graphs are going to cross on the screen. All right, so that's a big thing people forget when they're writing the solutions to a system. They'll write down the answer to one of the variables, but they'll forget to write the answer to the other one. So if I ask you for a solution, you should have an x and a y value. Now, if we were graphing 2 lines, how many solutions could you have at most? Looking for where they cross. Jack?
1.
Yeah, you could have 1 at most. Is it possible you get 0? Sure, you could get 0 solutions if you graph parallel lines. How about like a parabola and a line? How many times could they cross? At most. Twice. Yeah, parabola and a line could cross twice. It could cross just once or not at all. So depending on the complexity of the problems, you can get more than one solution. So as I already had said, to solve a system graphically, you're just looking for where they cross. Okay? You're trying to find the points of intersection. Okay. Does anybody remember on the calculator how you find intersection points? Like the buttons. What do I have to press to do that?
Second, calc, intersect.
Yep. So when we're looking for points of intersection, we're going to go second, calc, and then press intersect. Right, so second, calc, and it's the 5th option on my calculator. Now, the only thing that's a little time consuming about that is you have to do it for every intersection point. Okay? So in this case, the guess will be important. Okay? Remember, the guess will always, wherever you put your guess closer to when you're finding an intersection point, that's the one it gives you. Okay, so any questions on kind of the general approach we're going to take to solve them? All right. So let's take a look at our first one. Okay, it says 2x plus 3y equals 5, and negative 3x plus 5y equals 21. Okay, before I type these in graph them, can anybody tell me what shape these both are? It's not written in the format we usually like it in.
Lines.
Yeah, they're both lines. All right, you don't have anything squared. You know, like if you start putting in x squared, that's when you get parabolas, stuff like that. But we just have an x and a y, no exponents, except a 1. Now, what's the problem with both of these? If I want to type them in and graph them, it's not quite ready to do that. I've got to do a little bit of work first.
It's not in standard form, right?
Right, we got to get it in standard form, which has which letter by itself? Y. Okay, on the graphing calculator, anything you want to graph always has to have y by itself. All right, so let's take each equation, and we'll get y by itself. Okay, what would be my first step in the top equation? To start.
Move y on, make isolate y.
All right, and what would you try to move away from y first?
2x.
Yeah, and how would you move 2x to the other side?
subtract 2x from each side.
Yep. So I'd have 3y equals. Perfect. And I'm going to write it exactly the way Adrian just said, because I like to have the x term first, because my goal here is to try to get y equals mx plus b. All right, and now I have that. And what would be my last step?
Divide by 3.
Yep, so we're going to divide everything by 3. So the 3y, the negative 2x, and the 5. Okay, so that's going to give me the answer of y equals negative 2/3 x plus 5/3. Okay, so that's what I'll type into y1. Okay, I'm going to do the same thing with the second one, just to get y by itself. Okay, I'm going to start this time by adding 3x. And that gives me 5y equals 3x plus 21. And Sam, what would my last step be to get y by itself?
You would divide by 5.
Yep, we're going to divide by 5. And that's going to give me 3/5 x plus 21/5. Okay, what's the number in front of x called? It's a coefficient, but specifically in a line, it's the coefficient that tells me the slope. And what about the number, the constant? That's my y-intercept. All right, so the easiest way to type it in, I can go like this, negative 2x over 3. Okay, that's as long as you put the x in the top, or you could put it in front of the parentheses. Either way is fine. Okay, plus 5/3. And 3/5 x, so I'm going to type it as 3x over 5 plus 21/5. Now, before I hit graph, will these lines cross each other?
Yes.
How do I know they're going to cross?
They're not parallel.
Yeah, they're not parallel. Okay, and I know that because the slopes are different. Okay, so I'm just going to start with a standard window. All right, and they do cross. And I'm going to do what John said earlier to find where they cross. Second calc intersect. Pick a point on the blue, the red. And does the guess matter for this one?
I don't.
Okay, so some people say yes.
Yes, I guess matters.
Why does it matter?
I don't know.
I would say in this situation, no. I think some situations it would.
Some situations it does. This one it doesn't. How come it does not in this
In
one?
this one it doesn't because it only intersects at one point.
Right. Okay, the guess you have to put closer to the intersection point that you want. There's only one intersection point in this whole problem, so it'll automatically find it.
All right.
Okay? So x is negative 2, y is 3. So when you write your solution, what was y? Was it 3? You can write it this way. Make sure you write both the x and the y. Or you can write it as an ordered pair. Either way is fine. Any questions on that one? All right, so the next one we're going to look at a little more complicated graphs. We have a cubic and a parabola, but it's already solved for y for us. So that's usually the harder part. So just type it in. Okay, and in this case, they don't want us to actually find solutions. What are they asking for?
The number solution.
Yeah, they're only asking how many times do these graphs cross. Okay. Is everyone okay with what's on the left?
What's the sign in front of that?
Positive 3. That's positive 3. All right, so let's type in negative x cubed. I don't think you're going to need any parentheses here. Okay, plus 3x squared plus x minus 3. And negative 2x squared plus 5. Yeah, and again, I'll do my standard window and see what it looks like. Okay, there's my cubic, the top one. There's my parabola opening down. That's the bottom one. So what's the number of solutions to this system?
2.
I heard 2. I heard 3. I only see 2.
It could be possible that they cross this further down.
Right, they probably cross again further down. I mean, I can kind of tell the red and the blue are getting closer. So
I can see that.
what I would do is set your y min at negative 40. I'm just guessing. All right, and I can see they are going to cross again. Okay, even though I don't know if I tried to calculate an intersect, if I could actually do it, because I'm not sure it's on the screen. So if you wanted to actually do the intersect, I would say that should work fine. Okay, but the point is, make sure you look off the screen. Okay, that third intersection point was kind of hidden till you zoom in a little bit. Okay. So any questions on that one? Now, let's say I gave you a problem on the test and I said find one solution to that problem. When you find your one solution, how many parts is your solution going to have?
2.
2 parts, right? Your solution is going to have an x value and a y value. Okay, you'd have to list both. So any one of these coordinates would be correct. Okay, and the last one we'll do, and that'll finish up 3.7, is this one we're going to do graphically and algebraically. Okay, did anybody remember how you solve a system using algebra? I'll give you a couple hints. Elimination is one method. That's not the best method for this problem. But there's another method when both equations are already solved for the same variable. It begins with an S.
Synthetic division.
Nope, not synthetic division. Substitution. Yeah. Okay, so substitution basically says just take what y is equal to. Y is x cubed minus x. And plug it into the other equation for y. Okay, so it's like you're setting the 2 equations equal. That's substitution. Okay, so if I do that, I get x cubed minus x equals 3x. And whenever we're solving an equation, we try to get a certain number by itself on one side. What number is that?
X.
Number.
Oh, 3.
Think of like when you're solving a quadratic. You like to get it equal to 0. Okay, that's the number. So how am I going to get this 3x on the other side?
Subtract 3x off each side.
So subtract it. And if I subtract it, John, what does that give me on the left?
X cubed minus 4x.
And now, what do both of those have in common?
X.
An x. So, Ian, do you remember the name of that thing I can do when 2 things have something in common and I take it out?
Factor.
Yep, we're going to factor. And Ian, can you tell me what I'm left with if I factor an x out of x cubed?
X squared minus 4.
Perfect. And now that's a difference of 2 squares. So what can I do with x squared minus 4 again? I can factor it again. Does anybody remember how that would factor?
X
Plus 2. X minus 2.
Yep, x plus 2, x minus 2. Perfect. So now, because this is a cubic, it factored into 3 factors, which it should. Cubics factor into 3 things. And now I set each factor equal to 0, and those are my solutions. All right. Now remember, each solution is a coordinate. So we're going to find all the x values first. What makes the first factor 0?
0,
How about the second factor?
-2,
And the third factor?
2.
2. Okay. But remember, again, these are points of intersection. So now we've got to find all the y's. How can I find the y values?
You plug
You
in.
plug it back in.
Yeah, you could plug into either one. You should get the same answer. I think the bottom one is easier. Bottom one says to get your y values, triple your x's. That's all you got to do. Okay. So what's my first y value?
0,
My second
-6,
and third.
-2. I mean, negative, I mean, 2, it means 6.
Yeah, I know what you mean. 6.
Sorry about that.
All right. So algebraically, if you're going to solve a cubic like this, okay, something special has to happen. Okay, just like it did here. Okay. When you factor it, you get a difference of 2 squares, or somehow it's going to work out nice. All right, now let's graph it and just confirm that those are the answers we get. So we got x cubed minus x. So x cubed minus x. Let's try not putting it in the exponent. And was it 3x? Was that the other one? Right, and do a standard window. You don't. I think that window we have makes it actually harder to see the answers. Okay, so there's our cubic. And that line does cross it 3 times. I can tell it crosses at the origin just by tracing 0, 0. That's a point on the blue graph. And then I can trace on the red graph and see 0, 0 is also a point on the red. So 0, 0 is a point on both. So it means they cross there. And I could do the same thing with -2, -6, and 2, 6. Any questions on that? No, my calculator, it doesn't like me. I have to figure out why. I guess I gotta hold it sometimes. I don't know. All right. So any questions on that? All right, so that's really it for section 3.7. Okay, just make sure you know how to calculate intersects. Make sure you look for things that happen off the screen. And when you write your solution, give me an x and a y value. Those are the important points. All right, so now the rest of the week, we're going to focus on chapter 4. Okay, in chapter 4, we're going to talk about what's called a rational function. Okay, so basically, think of like a rational number. Okay, rational numbers are fractions. So basically, we're going to look at fractions where what you have in the top and the bottom is a polynomial. Okay, so chapter 3, we looked at just polynomials. Now we're looking at dividing 2 polynomials. Okay, and when we do that, we get all kinds of interesting pictures. Okay, just to show you an example of a rational function, I'll come right back to this. That's a rational function. Okay, so is that one. Okay, polynomial in the top and in the bottom. Okay, anything that looks kind of like that, those are rational functions. Okay, that's a very, very simple rational function. That's the simplest one you can have, just 1 over x. Now I said something important at the end here. I said that the bottom polynomial can't equal 0. Why not? Why can't q of x equal 0? Yep.
You can't divide by 0.
Right, you can't divide by 0. So in any of the problems I just showed you, I never had 0 in the bottom. There's another example of a rational function. It's not one I'm going to do anything with at the moment. I'm just showing you another example. As we study rational functions, we're going to kind of break them down into different cases, and that's what we're going to do Tuesday and Wednesday. One day we're going to look at what happens when the exponent in the top is bigger than the one in the bottom, like this example. And then on another day, we're going to look at what happens when the exponent in the bottom is bigger than the top. Okay, so the first one is an example where the top has a bigger exponent than the bottom. And the second example is where they're the same. Okay, we'll look at that case too. Okay, and you're going to get some very interesting kind of graphs. Graphs you've never really seen in Algebra 1. Maybe, I don't know if you studied rational functions in Algebra 2 as in depth as we're going to do, but the graphing calculator is extremely helpful in this chapter. Now, when we talk about rational functions, we do have to be careful with the domain. For example, in the first one, the domain could be any number you want except one number. Because if you plug this number in, you'd divide by 0.
0, 3.
Positive 3. Okay, so the domain is any number that you want except 3. So something weird is going to happen at 3. Okay, it's not going to be a graph that's continuous. Okay, you're going to have to pick your pencil up and start over again if you try to cross the number 3. And we'll talk about what happens at the number 3. Because that kind of leads into the next thing here, which I pretty much already said. The domain of a rational function is any number that you want, except values that make the denominator 0. Okay, that's the only thing you have to be careful of when you're dealing with rational functions. Just make sure you don't make the denominator 0. All right, so we'll practice finding the domain. In fact, you guys already gave me the answer to this one. What's the domain of that rational function?
Any number other than 3.
Yeah, so there's a couple ways you can write it. Okay, you can write out that whole sentence that Adrian just said. All real numbers except 3. Or what's the other way we can write it? Using more symbols and less words. Okay, and do you remember how we write that? I'll give you a hint, it has this symbol in the middle.
X greater than 3, x less than 3.
Okay, you could write x greater than 3 or x less than 3. You could do it that way as an inequality. What I'm thinking of uses interval notation, but that is also correct. Yep?
Negative infinity up to and including 3.
You want to include 3?
I mean, not including 3.
Yep.
Excluding 3 and 3 not including 3 up through infinity.
Perfect. Okay. The only reason I mentioned doing it this way versus as an inequality is because I know on the test there's some multiple choice questions and they write the answer that way. All right. So any questions on that one? All right, let's try this one. What makes this one a little harder to figure out the domain?
The denominators are quadratic.
Right, the denominators are quadratic. So what can we do with a quadratic that hopefully makes the denominator a little easier to look at? Yeah, hopefully we can factor it. And if we can, then we'll be able to figure out the what the domain is. Okay, so as I start to factor that, Jacob, what's going to be my first term in each set of parentheses?
3x and x.
So if we were going to try to factor the top, yes. But how about we're going to factor the bottom?
Just x.
Yep, perfect. Just x and x. And Brad, how about my signs?
Plus and minus.
Yep, I'm going to have a plus and a minus. And we're looking for two numbers that multiply to give me 2 and subtract to give me 1.
Positive 2, negative 1.
All right, let's check it. Got x squared minus x plus 2 plus x. Perfect. All right, now we should be able to figure out the domain. Ian, what's my domain here?
X may not be -2, x may not be +1.
All right, so that's what it isn't, which is fine. Can you also word it and tell me what it is?
Negative. I don't write with the negative infinity, 2 plus infinity stuff.
You could do it as an interval, or you could just say it as a sentence, kind of like we did the last one.
X can be anywhere from negative infinity up to -2.
Yep.
X can be anything from -2, not including -2, up to 1, including 1.
All right.
X can be anything that is not, that is greater than 1, not including 1, 2 is.
Yep. And what do we want to make sure we put between each of those? Or, yeah, which union basically means or. And by putting that symbol in, we can understand that these are not coordinates. I think it's obvious the first one and the last one are not a coordinate. Okay. But that's your answer. Okay. Or if you wanted to put it as a sentence, it would be all real numbers except -2 and +1. Okay. Okay, actually, I think example C is easier than example B. This one, I'm not going to write out the answer, so let's just go through it kind of verbally together. What would my domain be for C?
Anything not including -2 and, I mean, 2 and -4.
Right, all real numbers except 2 and -4. Okay, any questions on that? All right. So the simplest kind of rational function you can have is just the reciprocal function. Okay, those other problems we just looked at in example 1, those were rational, but they weren't as simple as this one. Okay, let's take a look at what the graph of 1 over x looks like on the calculator. And I just want to make sure something is clear about this picture. Okay. On my calculator, it almost looks like it kind of stops on the y-axis going up and down. That shouldn't stop. Okay. This part should keep going up forever, and this part down forever. Okay, that's the graph of 1 over x. Is that a continuous function everywhere?
No.
No, it's not continuous everywhere. There's certain parts that are continuous, like you could draw between 2 and 3 or 3 and 10 or a whole bunch of points, as long as you don't cross 0. If you try to cross 0, then you've got to lift your pencil up and start again. So something is happening at 0. Okay, and there's a name for what's happening there. Okay. So let's look at what happens as x gets bigger and bigger towards infinity, or x heads towards negative infinity. Okay. What's happening to my y value as x gets bigger and bigger and bigger? What does it look like y is approaching?
Zero.
It's approaching 0. Okay, look at your fraction. Ask yourself, well, what happens if you plug in a big number for x, like 1,000? 1 divided by 1,000, it's 1/1000th. Okay, very small. Right? If x is 1,000,000, to calculate your y value would be 1 divided by 1,000,000, 1/1,000,000th. Okay, so as you get bigger and bigger heading towards infinity, y gets very, very small, but it's still what kind of number, a positive or a negative?
A positive.
It's a very, very small positive number.
So if x is really close to 1, then it's more likely a value of 1, right?
Yeah, if x is 1, y would be 1. That would be a point on this graph. Yep. We're going to talk about what happens as x gets closer and closer to 0 next. Okay, but I'm gonna hold off on talking about numbers close to 0 for now. What about as x heads towards negative infinity? What happens to my y value there? It still gets closer and closer to 0, but this time it's not a positive number, it's a very, very, very small negative number. Okay, so in both cases, as x heads towards infinity or negative infinity, f of x, or y, is approaching 0. Will it ever reach 0? No. No matter how big you let x be, it's still 1 divided by something. Even 1 divided by 1,000,000,000. It's not 0, but it's small. Okay, and if you get this kind of behavior where x is getting bigger and bigger and bigger, and y is getting closer and closer to a number, but it never reaches it, that's called an asymptote. Okay, specifically, the first one we're going to look at is called a horizontal asymptote. Okay, and to find a horizontal asymptote, what you do is let x get really, really big and see if y is approaching a number but never reaching it. Okay, the way you could tell that on the graphing calculator is you can go to like your table, press second table, and then plug in a really big number for x, 0.002. Okay, let's go even bigger, 5,000. And now it's writing it in scientific notation, 0.0002. All right, so it's just a very, very small negative number, a positive. Right? And if I start to look at the other side, negative 1,000, it's negative 0.001. Okay, so it's getting very, very close to 0, but it's never reaching it. Okay, both of these graphs are examples of horizontal asymptotes. Okay, the second one, or the first one, is pretty typical to what we just saw in the graph of 1 over x. Okay, it's getting closer and closer and closer to a value, and it never crosses the asymptote. In the second one, it does. Okay? It's okay to cross an asymptote. You're not looking at what's happening near the origin. Okay, when you're looking for a horizontal asymptote, you're looking at what's happening as x is like 1,000 or 10,000 or 1,000,000. Okay? If it's crossing it when you get out that far, then that's a problem. Okay? But if you start heading out and it just keeps getting closer and closer and closer, that's an asymptote. Based on this picture, I would say the dotted line is an asymptote. To me, it just looks like it's getting closer and closer. Okay, and when we do our sketches, okay, what I'd like you to do is when you have an asymptote, just draw it as a dotted line. Okay, and page 217 has these same pictures I just drew if you want to look at them, and it explains them a little more. All right, so what they're doing in this one is giving us an expression, 1 over x plus 2, and asking us to find the horizontal asymptote. Okay, this could be written like that, or it could be written y equals, could be f of x equals, anything like that. All right, so first thing I'm going to focus on is the fraction. And I'm going to ask myself a question. What happens as x gets really, really big? What happens to this fraction?
It's small.
It gets very, very small. And what does this fraction approach? It approaches 0. Okay? As x gets bigger and bigger, try plug in 10 for x, you get 1/10. Plug in 1,000, you get 1/1000th. Plug in 1,000,000 for x, you get 1/1,000,000th. You're getting a very, very, very small number. But then what are you adding to that small number? 2. So as x gets bigger and bigger and bigger, what is y going to approach in this problem?
1,000 plus 2.
What is it?
1,000 plus 2.
Well, 1/1000th plus 2,
Yeah.
which is what?
2 and 1,000.
2 and 1 was like 2.000 or 2.001. So this is getting closer and closer to what number? 2. Right? If you were to graph this, it's going to approach the number 2. Right? So we say the horizontal asymptote is at y equals 2. And you could try the same thing if you plug in like negative 1,000 for x. You get negative 1/1000th plus 2. So that's like 1.999. Okay, again, very, very close to 2. Any question how I found the horizontal asymptote there? Now, what if I change this 1 to a 12? It's still the same thing, right? If you take 12 and divide it by 1,000,000, it's not really that much different than taking 1 and divide by 1,000,000. It's still going to be a very, very, very small number. So the point is, anytime you have an x in the bottom of a fraction, that fraction always approaches 0. And all you have to do is look at the stuff that's outside of that fraction. Okay, so what would my horizontal asymptote be here? What is it, Ian?
-3.
Yeah, -3. All right.
Signal to the
Because when you divide, when you have 1 and you divide by x, this fraction is just going to get very, 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 very small, very close to 0. And if you take a number close to 0 and subtract 3, it's very close to -3. Any question on that? What if I did that? What would the horizontal asymptote be now?
Still the same.
It's still the same. Okay, you're still taking 1, but instead of dividing by just x, now you're dividing by double x. So if you plug in 1,000,000 for x, it's like 1/2,000,000 minus 3. Okay, so that doesn't change anything. If you change the number outside, it does. All right, so let's take a look at that one that we did, and let's graph it. Somebody remind me again, where was the horizontal asymptote for this one? 2. So what I'm going to do is put a line in at 2. That's a line that I'm going to get closer and closer to, but I'm never going to reach. Right? And what I'm going to do is, actually, you know what? Because the arithmetic's pretty simple, I don't even think I need the calculator. Let's just test some points, okay, and see what it looks like. What do I get if I plug 1 in for x? What's 1 divided by 1? Plus 2? 3. So the point 1, 3 is on this graph. All right. What if I did 0.5? What's 1 divided by 0.5? 2. And then plus 2? 4. So 0.5, I'm up at 4. What if I took 1 and divided by 1/10? What's 1 divided by 0.1? 10, and then plus 2?
12.
12. So as I'm getting closer and closer to 0, all of a sudden this graph is going way up. Okay, we'll talk more about that in a second. Now, let's head further to the right. Okay, let's try 10. 1 divided by 10 is how much? 1/10 plus 2? 2 and a tenth, or 2.1. So when we go out to 10, just a little above 2. Okay, so basically it's going to look like this. It's going to come down, curve, and then get closer and closer to the asymptote. Okay, any questions on that section? Now, down here in the lower left, it's basically going to be a mirror image, okay? Except it's going to be kind of going down as we get closer to the x-axis instead of up. Right, so you could try a point. Try 1/10. You're still going to get, or negative 1/10. You're going to get negative 10 plus 2 is negative 8. So it's going to be heading way down. Let's try negative 1. Okay, what's 1 divided by negative 1? Negative 1 plus 2? 1. So negative 1, 1. That's a point. And I think that's pretty much enough. Okay, so as it comes up, it's going to look like this. It's going to curve and just keep getting closer and closer. Okay, any questions on that section? Yeah.
So how would you move like the line of symmetry vertically? Like the vertical line of symmetry, could you move it like left and right?
Mm-hmm. Yep. We can definitely move left and right. So anybody have an idea of how we do that?
You put a factor in front of like 1x or something like that. Like it'd be like 2, 1x plus 2.
All right, if you put a factor in front, that's going to be a vertical stretch. So anytime you multiply by a number in front, that's a vertical stretch. If you add or subtract a number at the end, that's a shift up and down. Does anybody remember how we shift left and right? We did it with parabolas. So this would be like a shift up. How would you shift a parabola left to? You put it in parentheses, right? Like this. And what would you put to go left?
X plus 2.
X plus 2. That's a shift left to. You could do the exact same thing here, except instead of being in parentheses, it's inside the denominator. Okay? And something like that would shift it left or right. Okay, we'll take a look at that in a second. Okay, so that's kind of getting at another type of asymptote, which we're going to talk about right now. Okay, let me bring up the graph again of 1 over x. And this time I want to know what's happening as x is heading towards 0, okay, from the positive side. Okay, so what's happening to my y value as x is heading towards 0 from the positive side? Yeah, it's approaching infinity. Okay, this is the positive side, okay, on the right. And as you start to head towards 0, all of a sudden the y value heads up. Okay? It just increases forever. And this is the notation you can use to write it. As x approaches 0 from the positive side, y approaches infinity. Okay, and I also want to look at the same question as x approaches 0. This time, what do you think that little minus means?
From the negative side.
Yep, from the negative side. So what's happening to my y value as I approach 0 from the negative side? about, Curtis? What's happening to that y value as you approach 0 coming from the left?
It's decreasing.
Okay, what's it decreasing to? So it's
0, or, I mean, negative infinity.
yeah, it's just going to go down forever. Okay, so as you head towards 0 from the negative side, the y value is going to approach negative infinity. Okay, and anytime that happens, that's something special. Right? As you approach a specific number from the left and from the right, if all of a sudden your graph goes towards infinity on one side and negative infinity on the other, okay, that's called a vertical asymptote. Okay, we had that in the graph of 1 over x. I didn't talk about it or show it to you, but if I wanted to, there's your vertical asymptote right there. Okay, so now when we graph something like this, we'll show both. Okay, so key to finding a vertical asymptote, it's got to head towards infinity on one side, and it's going to head towards negative infinity on the other. That's what I just said. Now, the vertical asymptote doesn't always have to be at 0, because, as Luke said, we can move that left or right. Okay, and it can be at a different number. Okay, and vertical asymptotes are pretty easy to find, okay, because they're the values that make the denominator equal to what number, do you think?
0.
Right, they're the values that make the denominator equal to 0. Right? So if you have a problem where it asks you to find the domain, you've already found the values that make the denominator 0. Now, does anyone remember why I'm saying this? No common factors in the top and the bottom. Remember what happens if you were to graph something like this? Let's say x minus 2 over x plus 3 divided by x minus 4 over x plus 3. Okay, if you graph what I just wrote in blue, there will be a vertical asymptote at 4. But there will not be a vertical asymptote at negative 3. Something's still going to happen at negative 3, but it's not going to be an asymptote. Does anybody remember what happens if you have a common factor in the top and the bottom? Right, it's basically like they cancel each other out. And what does that look like on the graph?
A hole.
It's a hole. Okay? So that's why I say no common factors. Okay, so find the zeros of the denominator and make sure that there are no common factors in the top and in the bottom. If there are no common factors, then your zeros of the denominator are your asymptotes. If there is a common factor, then the 0 is a hole instead. Okay, really important thing when you're finding vertical asymptotes, it's no longer y equals and then a number. Y equals is a horizontal line. How does the equation of a vertical line start? What letter? It's always x equals. Okay, and that's a mistake that usually trips some people up on the test. They figure out the number that they should, but they write, for say a vertical, they accidentally write y equals. Vertical lines are not y equals. Okay? They're x equals. Right? So what value is going to cause my denominator to be 0 here? 2. Okay. Do I have an x minus 2 in the top? Nope. There's no common factor in the top and in the bottom. So that is my vertical asymptote. All right, how about this one? Remember, just focus on what you need to. There might be some more stuff there that's irrelevant to what I'm asking. Okay, what's the vertical asymptote here? Careful, not 3,
Negative.
-3. And, well, if you plug in 3 in the denominator, you'd have 3 plus 3 is 6. Can you divide a number by 6? Yeah, dividing by 6 is okay. So you have to figure out what would cause this to be 0. And it would be -3 plus 3. And that would be 0. And should it be x equals or y equals for vertical? X. What does this -1 affect? Not the vertical asymptote. It affects the horizontal. Yep. Okay, so any questions on that one? All right, so I'll just graph one of these real quick and then we'll look at our last type of problem like this. Okay, so the first thing I like to do when I graph one of these is graph my asymptote. Okay, we already said, I think in this problem, that it was at 2. Okay, so draw your vertical asymptote at 2. Horizontal asymptote is at 0. And whenever you sketch one of these graphs, it's usually in the upper right and the lower left, or the upper left and the lower right. It's always in two of the sections. And to figure out where it is, I'm just going to type it in, but I'm not going to graph it. I'm just going to use the table. Okay, so first, in my table setup, I'm going to make sure it's set up exactly like that. Otherwise, this won't work. So make sure your independent is on ask, dependent is on auto. Go to table. And now I want to pick values for x. I can't pick 2, because that would cause me to divide by 0. But what's a number extremely close to 2?
1.9.
Sure, what, even closer?
1.999.
Sure, 1.99, that's good. So if I plug in 1.99 just before 2, I'm way down at negative infinity. Okay, what's a number that's just after 2? Even closer. Closer than that.
2.0.
He's getting farther.
Yeah, 2.001 or 2.01, that's fine. Okay, we're way up at 100. Now what I'll do is plug in a number farther away. Okay, I just kind of get the behavior near my vertical asymptote. Let's plug in a number like 500. Okay, what am I approaching? 0. And negative 500, what am I approaching? 0. Okay. So that one was just barely negative, just barely positive. Okay, so just connect those dots and make sure it doesn't cross the asymptotes. And there's your graph. Okay, any questions on that one? Okay, the only other kind of problem they can give us is something like that. And the reason this one's a little bit tricky is because whenever you want to look at a rational function, you always want to have it as a number, okay, over, and then you want an x in the denominator with just a number. So something like this. Okay, that's how you want it to be written. You don't want an x in the numerator. Okay, that's going to mess us up. And then you could have plus or minus a number on the end. Okay, kind of like I had in, I think I did one right here. That's the format that you want it written in. A number over just an x in the denominator, and then plus or minus a number at the end. This I can't really explain to you what's happening. Okay, what operation is it telling me to do with these two things? Divide them. So let's divide them. And when we're done, we're going to end up with something in that format. Okay? So I'm going to use synthetic division because it's faster. What are my coefficients? There's only 2 of them this time. 2 and negative 13. Okay, so I'm going to bring down my 2. 5 times 2 is 10. And what's negative 13 plus 10?
3.
Negative 3. That's my remainder. Okay, so when I do this out, that's my quotient. So I get 2. Now my remainder is negative, so I'm going to put minus 3 over my divisor. That's how you always can write it. Quotient plus remainder over divisor. Okay, we looked at that last week. Now this isn't quite the order that I told you it would be in. If you want to put it in that order, just write it like this. And now it's exactly what I have up above. So what I want to do is describe the transformations that are happening here. Okay, I'll do the asymptotes and then I'll let you guys tell me the transformations. So my horizontal asymptote is at y equals 2. And my vertical asymptote is at 5. First transformation you start with is always the one that's inside the function, the denominator. What's that minus 5 going to do?
Shift it right 5.
Yep, so shift right 5. Now the next thing we want to deal with is the numerator. Now there's 2 things happening in the numerator. Let's start with the 3. What's that 3 going to do? If you're not sure, maybe think of it this way would be helpful. So instead of putting the negative 3 in top, I put it in front. That's a stretch. Okay? Usually with this kind of function, they just throw the 3 in the top because it's a little shorter to write it that way. But that's a vertical stretch by a factor of 3. Now, we also have a negative with the 3. What does a negative cause to do? Think about like x squared versus negative x squared. What would the difference be? Yep.
Which is this stretching it, would shrink it, like compress it down?
No, the stretching and compressing is just that number. The negative is a flip. Yeah, it's a flip. And since it's with the number that does the vertical stuff, it's a flip vertically. Okay, so that's a flip over which axis? Yes. Okay, that's a flip over the x-axis. Okay, it's exactly the same stuff we did with parabolas if you want to check back in your notes. So flip over x-axis. And lastly, what's the plus 2? Shift there which way? Yeah. How many? 2. Good. Shift up 2. Hey, so any questions on that one? All right, so let's go do our last problem. This will be it. So last one we're going to look at, we're going to need our calculator. And it's a type of problem we might have looked at before. We're going to be mixing 2 things together. But a lot of times when you do mixture problems, you're solving a system. Okay, we're not going to solve a system. So I think it's a little easier way to look at a mixture problem. Okay. as we do it, the first thing I need to make sure everybody understands is this idea. If I told you you had 50 ounces of liquid, okay, in front of you, and out of that 50 ounces, 35% of it is acid, how would you figure out how much acid is in there out of the 50 ounces? 50 times what? Yeah. Okay. So we're going to have to do that in the problem. So if you've got 50 ounces of liquid in front of you and 35% of it is acid, take 50 times 0.35, and that's how much out of the 50 is actually acid. Okay, the rest might just be water or other stuff. Any question on that idea? Okay. All right, so now our problem says that we are going to add X ounces of pure acid to the solution I have up above. Okay, so 100% pure acid. That's what we're going to add into our solution. Okay, what I want to do is find a graph that represents the concentration. Okay, because obviously as you add more and more acid to your solution, you're making the concentration of it higher and higher. How do you find a concentration? Like if I said to you, I have a solution, it's 40 ounces, 10 ounces of it are acid. How strong is it, like percentage? What do you do with the 10 and the 40? Yeah?
Divide.
Yeah. If you had 40 ounces and I said 10 ounces out of that is acid, take 10 and divide by 40, and you get a concentration of 25%. So to find the concentration, you have to take, it's the part over the whole, or part over total, okay, when you learn percent. Take the amount of acid and divide by total amount of stuff. Okay, so in my solution, I have 50 ounces, and it's only 35% strength. So how much acid am I starting with in my solution? Well, Ian? It's the same one we did up above.
Sorry, I just lost the last two words of the question.
So how much acid am I starting with in my solution?
17.5 ounces.
Yeah. Okay, we're starting with 50 ounces, only 35% of it is acid, so we're starting with 17.5. And how much pure acid am I going to add to that? X. Okay, and we're going to divide that by the total. Okay? So how much stuff am I starting with?
50 ounces.
50 ounces. And how much stuff am I adding to it? X. That's a graph of the concentration. Okay, what is my concentration starting at? What's the percentage? 35%, which is what as a decimal?
0.35.
All right. Can the concentration go any lower as I add pure acid? No. But it can go higher. What's the highest my concentration could approach?
100%.
Okay,
It would
would-
be unattainable highest.
How come I could never reach 100% if I keep mixing more and more pure acid? Yeah?
Because there's still non-acid in the mixture itself.
Right. You started with a mixture that wasn't pure, so I don't care how much pure acid you keep adding. It's never going to be 100% pure, but it'll get higher and higher. And let's say we add up to X is how many ounces of pure acid. I'm just going to say 300. So there's a graph of my concentration. Notice what happens as you start to add more and more acid. Eventually, it doesn't really have that much of an effect. Okay, the concentration comes up a lot at first, but then it levels off. So that's a graph of my concentration. Okay, and I'm gonna stop with that. Okay, so there's a problem like this in the homework. We'll go over that one again just to make sure people understand it, because that's an important one for the test. All right, so the homework, the first part is on solving the graphs and where they intersect. That's on page 208, numbers 8 through 10. And then on page 222, okay, 3 through 7 odd, 11 to 21 odd, 23, 31, 37, 38. And then on 48, this is a little different than what I normally do. I think there's multiple parts. I don't want you to do the whole question. On 48, just do part A and part B. Don't do part C. Okay, so we'll take a look at that first thing tomorrow, especially that word problem, make sure we're okay with it. And the next 2 days, we're just going to do half a section each day, so we're really going to slow down quite a bit.